The last lesson of this chapter is called Additional Properties of Binomial Distribution. So just a few more things that I have to teach you about those binomial probabilities. We'll start with a probability distribution. You have a 25% chance of guessing correctly on a multiple choice test. Let's graph that entire binomial distribution for answering 4 multiple choice questions. So we're talking about n equals 4. Which means for this discrete random variable, I could get 0 right, or 1, or 2, or 3, or 4. And there is a probability for getting each of those numbers correct. Remember that I can use the formula, I can use the binomial PDF, or I can use the table. My preference when I'm filling out a table is to use the table, so I'm going to try that. On this problem, we have 4 multiple choice questions. Our probability of guessing correctly is that 25%, and I want to fill out all of 0 through 4, don't I? So I'm going to be following that graph over, and here are the numbers that I want to enter into that table. All right, you can see that it's most likely that I would get 1 question correct. I've got a 42% chance of getting 1 out of the 4 correct. And I suppose that makes sense because I have a 25% chance of guessing correctly. I put the values for the random variable across the x-axis, probabilities up the y. And this graph just shows again that my best chance is to get 1 out of the 4 right. And do you know what they call that? They call that the expected value, or the expected number of questions that I should expect to get right. And do you remember how we calculate expected value on probability distributions? We take the x times the probability, the x times the probability. We would multiply each of those and then add them all together. And in this case, I did the math, they all add up to equal 1. And so that is my expected value on this. I'm going to show you a shortcut a little bit later. Let's see how that distribution changes if you aren't just purely guessing, you know enough to eliminate 2 choices on each question. Now you have a 50% likelihood of guessing correctly. So if we had 4 multiple choice questions, how many could we expect to get correct now that we're having like a 50-50 shot at each one? Let's fill out our table. Again, there's still 4 questions, so I could get 1 or 2 or 3 or 4 right. And I will find the probability for each of those. Again, we're talking about n equals 4 questions, and my probability is the thing that changed this time. I've got a 50% chance of getting things right, and a 50% chance of getting them wrong. Again, I could use the formula or the button on the calculator. I prefer to use the table when I'm filling out a table. And the only thing that's changed here is that I'm looking at the different probabilities, so I'll be looking at these numbers instead. There's some nice symmetry there, huh? I just love the symmetry on that. What was it about this problem that caused it to be so nicely mound-shaped symmetric? Well, the only thing that changed was our probability, so I wonder if it's that probability being 50%. 50-50 shots make things pretty even. And what's my expected value here? It looks like my tallest bar, my highest probability, is the probability of getting 2, and so I would say that my expected value is answering 2 questions correctly. On this problem, they already made the probability distribution graphs for n equals 20 and n equals 50. And they were talking about us answering 20 or 50 multiple choice questions, and how accurate were they if we took these probabilities into consideration? What was our probability of guessing each question correctly? And our clue comes in that expected value. For this graph, it looks like 16 was my expected value. So getting 16 out of 20 right was what I expected because my probability, my accuracy was 80%. I was guessing 80% of the questions correctly. How about on the other graph, my expected value? Looks like it's 40 out of 50. So again, 80% accuracy. And you'll notice that both of these graphs are shaped similarly, right? Aren't they very skewed? What do we call that? Skewed left? Skewed left. They really have the same shape. And I should say that these two graphs wouldn't just apply to 80% probability on a 20-question multiple choice test. This would apply to any situation where we were talking about 20 trials and a probability of success of 80%. Earlier I had told you about a shortcut for those formulas, but there is one catch. It only works for those binomial probability distributions. The shortcut only works for those. If it was some other sort of probability chart, probability distribution, then you'd be stuck using these more complicated formulas. But if you're lucky enough to have a binomial situation and they ask you for an expected value, it's going to be a quick calculation. Here I've got let's say a 20-question multiple choice test, or I'm guessing with 25% accuracy, and there are my chances of getting X problems correct out of 20. What I'd want to do is to calculate that expected value. All I have to do is take n times p. N is 20 and p is 0.25, and so that comes out at 5. If I'm guessing a quarter of them correctly and I answer 20 problems, I should expect to get 5 correct. And you'll see that that is the highest bar on my probability distribution. The expected value is 5. Now, even better than that is the standard deviation formula. How much simpler does that look? Before, I was making these terrible charts and adding things and squaring things. It was awful. But if I'm lucky enough to know that it's a binomial situation, all I have to do is take the square root of n times p times q. Love that. Remember, standard deviation just tells me about the spread of the data. Sometimes I'm going to get 8 out of 20 correct, sometimes I'm going to get 1 out of 20 correct. But on average, I'm going to vary from the mean by about 1.9 questions. And that's really it. I just wanted to focus a little bit more on expected value and give you those nice shortcut formulas, only useful for binomial probability.